Good afternoon, everyone. So I'm presenting this paper, Improving Word Alignment Using Word Similarity on behalf of Theerawat, Songyot, and David Chiang, as they are not able to attend the conference. And if you find this work interesting, please feel free to email the authors for any questions that you have. I'm pretty sure they'll be very happy to answer your questions. So this paper aims to improve word alignment, which is the basic building block of the state-of-the-art machine translation system. And I will start the talk by briefly describing what the word alignment is. So the problem of word alignment is that you're given a pair of sentences into different languages, as shown on the top of the slides here, and you want to find the word level translation correspondences between the sentences, as shown in the correspondence are displayed as the links here. And we want to do this automatically and accurately on a very large amount of data. So this is already a well-studied problem. And the most widely used methods include the IBR models and HMM-based models, and which are proposed almost like 20 years ago. And since then, there are many work that try to improve the word alignment. For example, Yamada and Kevin apply syntactic constraint to the alignment model, and Ashish Vaswani applied like L0 prior to encourage the sparsity in the lexical translation model. And of course, there are many more nice work besides those. We could roughly divide the previous work into two categories. One that use more information or more knowledge, like syntax or part of speech, and the other makes some additional assumptions, like the sparsity assumptions in the using the L0 prior work. But in all the previous work, the word alignment models are all built upon the lexical translation model here, which is probability of F given E, which is the probability of the word F being a translation of the word E. And they are modeled as the categorical distributions, which mean they are basically estimated based on the co-occurrence of the word F and the word E. And this also means that each word is independent of each other. And even you're given two synonyms in English, and they will always be unrelated, and they don't share any information between each other. So the one drawback of those previous models is that they have a problem when they see the real words. So here is the example. So we have two set of parallel sentences here. One is the leben and stay on the top of the screen, and they are only one word. And on the bottom of the screen, you can see another pair of sentences, which John wohnt hier nicht, and John does not live here. And the alignment for the first sentence pair is very clear, as though they only have one word. But suppose here we only see the leave here only once throughout the parallel corpus, and then how are you going to align the leave with the rest of the words on the other side? And here the answer is just to take the equal probability to align to each of the words. Because of this, then the word alignment models tend to misalign low frequency words. And this work aims to solve that problem by introducing semantic relationships. So this talk will be divided into three parts. So I will first discuss the intuitions and rationale behind the work, and then I will explain our word similarity model, which is a key contribution of this work. And finally, I will present some experiment results. So now let's go back to the previous problem. So suppose that now we have some additional information We know that the word Leben and Wohnt are semantically close. And we also know that the stay and leave are also semantically related. So does this extra information help you align the word leave to the rest of the words in the sentence on the other side of the parallel sentence? Yeah, the answer should be yes. So as we see the first pair, that the sum sentence pairs tells us that the word Leben and should be aligned to stay. Intuitively, we should increase the probability that the word leave is aligned to the word wohnt in the sentence, which is shown at the bottom of the screen here. So the idea is, in general, we want that the probability of a wohnt being a translation of leave can be increased or decreased by the information from their related words. So to achieve this, we essentially break down the probability and take in the summation over all possible E words and F words in the vocabulary, as shown in the chart here. And the equation is also shown at the bottom of the slides. So in this paper, we use this intuition and redefine the existing lexical translation model. So this works is simply a method to enhance the word-aligned models by redefining the lexical translation model. So what left here is really a model that can tell us whether two words like W prime and W here are semantically related. And we call this a word similarity model. Please note that we need one model for each of the language that we're trying to learn. But the good thing is that we can train models separately for each language and using only monolingual data, which is available in a much larger greater amount compared with parallel data. Okay, so now it's a good time to explain the word similarity model. So here is how we actually define our word similarity model. So for a given word W, the model defines PW prime, given the W, the probability that the word W prime might be used in the place of the word W. So here, when we say W prime is used in the place of W, we mean that for a particular context where the word W occurs, we can see W prime also in the same context, but in another place in the data. And to model this, there were two factors to consider. So first, when the word W occurs, it can occur in many different contexts. So we must consider how likely each of those contexts is associated with this W. And second, for each of those contexts, we want to consider how likely the W prime is observed when those contexts appears. And formally, we can define the probability as the following. So the word similarity model can be defined generatively as the summation over all possible contexts of the second term, the second factor here, which is P of context C given the W, which is the probability of seeing the context C given W, times the first factor here, probability of W prime given the context C. So by factoring, the benefits of doing this is by factoring the word similarity, we are able to train each factor separately and efficiently. So the second factor is pretty easy to compute. We can just model it as a categorical distribution and train it using the maximum likelihood estimation. However, modeling probability W prime given the context is a little bit difficult, as the number of possible contexts is exponentially large. For example, if you consider context with word window 10, the size of a context is equal to the vocabulary size raised to the 10th. So there will never be enough data available to train this. So instead, we use using a feed-forward neural network to model this problem. So at the bottom is the input layer, which is the sequence of words representing the context. And we use a shared projection matrix to reduce the number of network parameters. At the top is output layer. And due to the time limit, I'm not going to talk about the details of the neural network. You can find the details in the paper. And also the structure of the network is not new. It has been successfully applied for language modeling, and it could be trained very efficiently using noise contrastive estimation. So on these slides, there are some examples of word similarity derived by our word similarity model trained on English gigawords. So we took 5 most similar words for W prime for each of the example. So in this table, it's very interesting to see how similar those words are, and their similarity can be measured quantitatively. So the property here are really normalized. So once we have these word similarity models, we can use it to extend the lexical translation model in the system, our translation system. And this extension can be applied to essentially any word alignment models. In our work, we extended the IBM model 1 to 4 and the HMM model, and then we use this in all the experiments. And there are, of course, some technical details, such as how to reduce the computations, and all those details should be able to find in the paper. So now I will just move on to the experiment parts. So we trained the extended word alignment model for 2 language pairs. Chinese English, and which has about 22 million word tokens, and also Arabic English, which has about 10 million word tokens in total. And all the training data comes from the NIST 2009 constraint shared tags. And on the second row here, you can see that we take 1/8 of the training data to simulate resource-limited scenarios. And this size of the training data are practical and very close to the real low resource settings. And in the end, we also have a little bit of a hand-aligned data for each language for evaluating whether the system actually improved the alignment. So first of all, let's look at the alignment results. So this table shows that the alignment quality, as measured by F-score, is increased. We can observe that the system achieved 5 to 10 point improvement over IBM Model 4 as a baseline. We can see that the Chinese English, in the setting of the Chinese English resource limited, we achieved the largest improvement. And we will take a closer look at this setting. As a beginning, that we want to solve the problem of real words. So we want to see whether our model really did the job. So to look at this in detail, we group all the source words types by their frequency and calculate the F-scores for each of the groups separately. So as you can see, this bar chart shows that the gain for the low frequency words, which is on the left-hand side of the graph, is relatively large compared with those high frequency words. So for words with frequency less than 10, we achieve as much as 20 point improvement in F-score. So to evaluate the alignment quality extrinsically, we do machine translation experiments for each of the 4 data sets. So we use the resulting alignment to build a hierarchical phrase-based machine translation system. And those systems are tuned using the mirror on our tuning set, and the test is on 2 different test sets. So all the test sets comes from these 2004, 2006, and 2008 test sets. And here is the result from the machine translation experiments. So the table summarizes the translation quality as measured by the blue score. So under the resource-limited settings, our approach achieved 1.3 and on average over about 1 point blue score on 2 different test sets. And on a full data set, we achieve 0.6 and on average 0.5 blue score on different test sets. And all those improvements are statistically significant except for the Chinese English full data sets. And this brings to the end of the presentation. So in summary, we use the semantic relationship to share to improve the lexical translation model. And this idea can be generalized to information sharing among all the categorical distributions. We use the word similarity model to measure the semantic relationships quantitatively, and the model itself shows to help machine translation. And we're hopeful that this model can be useful in other natural language processing tasks. And this is the end of my talk. Thank you very much.
Same thing, we perhaps don't have the author, but
if you have any comment, maybe I can try.
Can be welcome. I don't know if it's a question or a comment, or at least we're probably naive enough for you to answer. The similarity is semantic. Would similarity of ether types be of interest, for example, morphological similarity between words?
You mean whether I look at the morphological similarity?
Yes, between them. Can other elements be used to sort of also add something as some extra similarity measure?
Yeah, we didn't do that. It's basically based on the similarity is solely based on the context. Yeah.
Okay. Yes?
In the paper, I saw that the new estimates are actually interpolated with the original IBM estimates, right?
Sorry, could you repeat your question?
You didn't have it here on the slides, but if I recall well, there was an interpolation.
Yeah, it's interpolation.
So I was wondering, that seems to defeat the purpose, right? I mean, it's not your fault, I know, but it's just a question I have. Do you have any thoughts about that, or shall I mail the authors for this question?
I mean, what's your question? Difficult?
Because I mean, the interpolation itself basically is taking the original counts, and it's only doing it for the low frequency counts. I think they're using Knesser and I again for the interpolation itself. So only the low frequency types are being influenced by this model. So I'm wondering whether, does it make sense to really kind of do it all the alignments in a frequency plus semantics way without this interpolation? I know the question is difficult, but I'm just wondering, like, we tried something similar, namely, and it's kind of,
Yeah, for that question, I think that's very related to the experiments part, so I probably wouldn't able to answer that formally here, but you are welcome to send those questions to you.
I'll mail
that's
them.
a good question, yeah.
Okay, thanks.
Yeah. Thank you.
Okay, well, thank the speaker again.